All right, today we're diving into something fascinating, a hidden challenge that comes with going green. It's a massive engineering puzzle that could literally determine whether the lights stay on in our renewable-powered future.
It's something we all take for granted, right? You flip a switch, and boom, the lights are on. But behind that simple action is this incredible high-wire balancing act between the power being made and the power being used, all happening in real time. So how on earth does it stay so perfectly stable?
Well, to understand where we're going, we first have to understand where we've been. The secret to all that stability is baked right into the old-school design of our power grid. You could almost think of it as having a giant, spinning, physical heartbeat.
For more than 100 years, the grid has basically been a network of huge, centralized power plants. Think coal, gas, nuclear, just pumping out electricity to everyone. And it turns out, this old design had a kind of secret weapon, a built-in safety feature that we're now about to lose.
And that secret weapon, it's called grid inertia. Simply put, it's the grid's natural, physical tendency to resist sudden changes. It's like a form of momentum that just keeps everything running smoothly, no matter what.
So where does this inertia actually come from? Well, it comes from these things. What you're looking at is a massive steam turbine rotor. I mean, these things are colossal, weighing hundreds of tons, and they're spinning at insane speeds, 24/7, deep inside our traditional power plants.
Okay, the easiest way to get your head around this is to picture a really, really heavy spinning top. Once you get that thing going, it does not want to slow down. It doesn't want to speed up. It just wants to keep spinning at that nice constant speed. That physical resistance, that's inertia.
And here's the magic trick. All that physical momentum from those spinning tops translates directly into electrical stability. It keeps the grid's frequency, its electrical heartbeat, locked in a super tight, safe range. So if a big power plant suddenly trips and goes offline, the inertia from all the others still spinning gives the whole system precious seconds to respond. It's the ultimate shock absorber. Okay, so we have this really stable, old-school system, but it's now facing these enormous pressures that are forcing a total reinvention. Let's take a look at why.
First up, just look at our appetite for energy. It's just going up and up and up. Projections show we're going to need a whole lot more power in the coming decades. It's not slowing down.
And then there's the big one, the really urgent reason. This graph shows the unbelievable rise in CO2 emissions. And where is it coming from? The very same fossil fuels that spin those giant turbines. We can't keep doing it this way. The need to decarbonize is absolutely critical.
And so the great transition is already happening. Look at that green line for renewables. It's on a path to completely take over our energy mix. This is not an if, it's a when.
But here's the catch, the big unintended consequence of this amazing green revolution. As we switch off those old power plants, we're also switching off their inertia. So what happens when all those giant spinning tops just stop?
We are fundamentally changing the blueprint. We're going from the model on the left, a few huge spinning generators, to the model on the right, with millions of smaller, spread-out sources like solar panels and wind turbines.
And this is the absolute key to the whole puzzle. Solar panels, they don't spin. Wind turbines do, sure, but they're not locked into the grid's rhythm in the same physical way. Instead, they both connect using power electronics, basically smart converters. And those converters, they have no physical mass, no spin, and therefore zero inertia.
And this isn't just a wild theory. The people who run the grid, the engineers, the system planners, they all agree. The consensus is clear. The future is going to be dominated by renewable energy sources.
So, what's the bottom line? A grid dominated by renewables means a grid with way less physical inertia. We are systematically removing the system's natural, built-in shock absorber.
Right about now, you're probably thinking, okay, so what? Big deal. It's just different tech. But why is losing this inertia so incredibly dangerous for the stability of our entire electrical system? Okay, check out these graphs. They tell the whole story. Imagine a big power plant suddenly trips offline. See that yellow line? That's our old high inertia grid. The frequency dips, but it's slow, it's gradual. It gives the system time to recover. Now look at the blue line. That's a low inertia grid. The frequency doesn't dip, it plummets, falling way faster and deeper into the danger zone.
There's actually a technical name for this speed, rate of change of frequency, or ROCOF for short. A good way to think about it is how fast the grid's heartbeat can basically go into cardiac arrest. If that rate is too high, safety systems all over the grid can get spooked and start shutting things down, leading to a domino effect, a massive cascading blackout.
And believe me, this isn't just theoretical. This is real-world stuff. During the massive 2016 blackout in South Australia, the grid hit an incredible roke-off of 6 Hz per second. And what was the situation right before it all went down? Renewables were providing nearly half of the state's power. That event was a massive wake-up call for grid operators everywhere.
So yeah, the problem is very, very real. But you know what? It's also an incredible engineering challenge. This is forcing us to get creative and to invent a totally new, smarter kind of grid.
Look, we're not going back. We can't. The move to renewables is on, so the only path is forward, which means engineers are basically in a race to replace that old physical inertia with something new, something smarter.
And some of the solutions they're coming up with are just brilliant. You've got virtual inertia, which uses clever software to make solar and wind farms act like giant spinning machines, providing stability without the actual spinning. Then there's smart loads, which could turn things like our air conditioners and EV chargers into a giant distributed shock absorber. And with AI and new sensors, we can actually predict when the grid might be weak and measure its inertia in real time so we never get caught off guard.
So there it is. That's the engineering puzzle we're facing. As we build this amazing, clean energy future, we have to solve the inertial problem we created by leaving the past behind. The real question is no longer just about generating clean power. It's about whether we can engineer an entirely new, intelligent system that's not just clean, but actually smarter and tougher than the one it's replacing. Thanks for tuning in to this explainer.